Hey everybody, welcome to this tutorial. So today we're going to talk about nested tuplets, which is an idea that I learned about from Sam and Alex at Cycling74, who did this project called NestUp, which is a markup language for musical rhythms. And you can see it looks a little bit like this, and we'll talk a little bit about how to understand this. And our goal today is basically going to be able to recreate something like this, or kind of get at these ideas using the techniques that we've been exploring in the past in Max, using some of these new Max 8.3 objects and working with phasers. So what's cool, I think, in particular about this nested tuplet concept is the idea that it does not require us to default back to the same sort of metronomic subdivision of the beat that is normal in all other music. So if you look at a drum machine or you look at a piano roll, it sort of presumes that you're going to divide up the kind of time space into these equal blocks, whether those are bars or 16th notes or 8th notes or whatever. This idea gives you a lot more flexibility to kind of work with different types of subdivisions and experiment with some new ideas. And the way that it does that is it starts with this concept called a container. And this is sort of Alex and Sam's jargon here, which I actually think is very useful. If you can go look at these things in kind of like a musical notated sense. To me, personally, I don't really understand this very well. So to me, this kind of way that they explain it makes more sense. So we'll start with this idea of just 4 inside of these brackets here. And anytime you use these brackets, you're creating what they call a container, which is basically a sort of a segment of time, which always begins with a musical event. Actually, I need to mute these other ones. We're just going to work with the kick drum for the moment. So I hope you could hear that. Yep. And the number indicates the length of the container. When you sort of create your first container, you're working from the number of beats. So if I say 4, I'm just going to have one event every bar at 120 beats per minute. If I change this to say 2, I'll double the frequency at which that occurs. Another thing I can do, which is going to achieve the same result, is copy this example they have here. And now we have 2 containers, each that are 2 beats long. And then here's where we start to get really interesting. So in this case, we're going to have a container that is 3 beats long, and it has these subcontainers. The first one of which is 2/5 of the 3-beat container, so 3-beat parent container, and the second of which is 3/5 of that 3-beat parent container. And if you are a reader, I'll hover this here and you can read it up here in the left. So the way to understand this is we have one 3-beat container, which means, right, if I do this, if I say 4 here, the amount of time from the beginning of this to the end of this is longer when I put a 4 here. Having a problem with my headphone. Okay. And you can hear that because I'm basically making that parent level container 4 beats rather than 3. And then when it comes to these subcontainers, we're defining the length by saying, basically taking the sum of these 2 and then dividing each of them by that sum. So this first container is going to be 2/5 of the parent container, and the second one is going to be 3/5 of the parent container. And then the final concept is this idea of a subdivision. So with a subdivision, which looks like this, and uses these curly braces, rather than the number indicating the length of something, it's indicating a number of events that occur within a container. So in this case, I have a container whose length is 4 beats, in other words, one sort of normal bar, but we're going to have 3 evenly distributed events across it. So this is like a triplet. And it can get pretty complicated. And actually it hits a level where I sort of have a hard time even interpreting what's going on, and they have a sort of syntax for how this whole thing works, which I definitely recommend checking out. I'll post the link here down below, and you can buy the Max for Live device if you want to, and you should, because it's really great. But what we're going to do today is try to figure out how do we borrow some of these ideas and implement them using Max 8.3. Okay. So we're going to start, like always, with our phaser and transport combination. And we're running at 120 beats per minute today, and you can see we have our nice phaser. And just to start simply, we can use a rate object to create this first container. And because we know that the container number, the container length is counted out in bars, at least for this top level, we're just going to take our length, we'll call it first container length here, and we will divide that by 4. So if I wanted it to be 2, then I can do that, or 3. And if we go back to our example, I think this is a good one to try to replicate. So we have a container whose length is 3, and it has the 2/5 and the 3/5. So with this first one, it's easy, right? We made a 3-step container. And actually, we can just stick a what object here. And I have a little drum. And we can just pop a what object here, and great. So now we have the simplest thing. And let me just make it possible for us to turn that off. I guess I could have used the gain here. All right. And in fact, I'll just disconnect this for now. So now we actually need to be able to have 2 more containers, and that basically fit within this first one, right? So over the course that this goes from 0 to 1, we basically want to have the output, the result, be that we actually now get, in the time that this one takes to go from 0 to 1, we want to get 2 that go from 0 to 1, and we want that first one to go in 2/5 of the time, and the second one to go in 3/5 of the time. So if we just take those 2 numbers and we say 2, 3, and we take the sum of those, and then we divide each of them by the sum. And we want to use float division here, so I have to put an argument with a period in it. And then I'll just do a ZL group 2 for now. You can see we're getting 0.4 and 0.6. So in other words, another way to think of this is we want one phasor that's going to go from 0 to 1 in the time that it takes this one to go from 0 to 0.4. And then we want a second phasor to go from 0 to 1 in the time that this one takes to go from 0.4 all the way to 1, right? The remainder of the phasor. So there's kind of two components that we need here. The first is we want to basically identify this point at which each of the sub-containers or the sub-phasors starts. And the way that we could do that is with a what tilde object. So we could say, we could add up these values. So let's use a trigger object so that our patching is nice and clean. And I'm also going to add a bang to the beginning and a 0 to the end, and you'll see why in just a moment. And the bang is going to be to bang this ZL group when the whole process is done, because I'm definitely somebody who likes to just bang my ZL groups rather than giving them a length. And then the other thing that we're going to do is we're going to add up these values so that we're going to get like 0.4 and then we'll get 1 instead of 0.6 because it's telling us those points along the way at which those phasors need to begin. And if we had something like, say, 235, right, we would have actually multiple points along that, more points along that ramp that we want to capture. So we want this to be extendable and actually work regardless of the number of events that we have or of containers that we have. So in order to do that, I'll add a little accumulator here. And if I just do that, I have to, this is an integer, needs to become a float. There we go. All right. So now we have 0.4 and 1. And just for argument's sake, if I said, 0.236, just as an example, we would get what those points are along the array. 0.235 is probably a little easier to understand because they add up to 10, right? And then I can basically just pass that into a what object, except I do know that what doesn't love to receive 1. It really prefers 0, and 0 and 1 are right next to each other. So what I'll probably do, knowing that the first, the 0/1 is always going to be kind of where that first one starts. What I'll do is I'll just say ZL equals 1, which is going to allow me to take that last item off, and then I'm just going to prepend it with 0. And then I'm going to pass my rate object into that. So if we do our go back to our standard 2-3 example, we should get an impulse from this what object at the beginning of the phasor ramp and then 0.4 of the way down, which we do. So then the next thing that we want to do is basically at these points start new ramps. And there are a couple ways that we can do that. There is an object called ramp tilde. The only issue is that it wants a millisecond duration argument. So like if I say ramp 100, that's going to be a ramp that goes from 0 to 1 over 100 milliseconds. It doesn't really... we might be able to get it to work, but it would be kind of confusing because we're not really working with milliseconds here. We're working with subdivisions of things. So I think a better approach would actually be to basically take what we're getting from this ramp and actually take the delta, which is the difference between one sample and the next, which I can show. And this is actually a very small number. It's for every sample that we receive here, It's the difference between the current one and the prior one, right? And I could actually make, just for argument's sake, I could make a phasor by saying, give me a signal of 1. So we're just going to get constant 1 every sample. And then if I know the sample rate of my, what is it, DSP state? If I know the sample rate of my audio system, which I can get from right here, and then I multiply that, we take 1 over that, and just multiply it by our sig here. We could also just pass, actually, that's even better. Right, so now we're going to get the value, whatever the sample rate is, probably 44,100 over 1, and we're getting that one of those every sample. And then if we just add those up and then take the modulus of 1, oops, we need to do signal modulus. That's a 1 Hertz phasor. So what we're basically doing is we're just adding up a very small value, 44,100 times a second. And in this case, that value happens to be 1 over 44,100, which means that this thing is going to go from 0 to 1 every second. So we're going to basically do a similar thing here, right? If we were to change the value that we have coming in here. So if I were to get rid of this part and I were to do something else, like something higher, some higher number, like 0.002, I'm going to get a faster wave out of that. So what this allows us to do is basically we can take what we're getting from the current parent container and basically scale that in order to get a new phasor at the speed that we want. So what we, just as an example, so we have 2 and 3, right? And we already know that 2 and 3 are 0.4 and 0.6 of 5. And so we are going to take 0.4, and then we'll do that over 1, or 1 over that. Which is going to give us 2.5. And we're going to get a little bit of a weird result. And the reason is because the delta does include a -1 somewhere along the way. Because this input phasor goes up to 1 and then back down. So it messes things up. So one thing I need to just do is say, if that phasor signal is greater than or equal to 0, then let it through. And if not, not. And then, of course, we need to accumulate. And then we also need to take the modulus of 1. So now we have a phasor that is 1/4 of, or 4/10, 0.4 of the input. And this is basically what the rate object does, right? So now we basically just need to get this. We need to get these two things working together, basically. We need to know, well, what of those ramps should I be on, which this what object can tell us. And then we just need to pass the correct corresponding value into our little rate modifier here. And then that's going to give us phasors that are subdivided the correct amount. And a way that we could do that is with stash. So basically we'll hold on to these values. And I think a good place to do it could be here. So we'll add another Zeal group here and bang that and then send that into the stash. So the result I'm going to get will look like this. Wait, sorry, here. 0.4 and 0.6. And actually, if we wanted to, we could just completely prepare it for ourselves. So we could say, we could take those 1 over those values. So now we have those values that this rate thing is going to need, and we can just connect our stash to that. And then we're going to give this mode 1, which means that when I pass a signal into the third inlet, it's looking for an index. So we have a 2-item list basically stored inside this stash object. And so if I send 0, it's going to give me 2.5. If I send 1.6, or sorry, if I send 1, it's going to give me 1.6 repeating. So now we can use this what object to basically count out how many of these events have occurred. And one way I actually might do this, just to clean things a little bit, is take away our prepend 0 here and rely on a second what to identify that 0 point. Because if I just make a new what object, vanilla without sending anything into it, just a signal, it's going to give me impulses on by default at the beginning/end of each phasor, right? And so what that actually allows me to do, if I just send the 0.4 onto the first what object, or basically, if I had a longer list, as an example, it would be the first n-1 values where n is the length of the list. And we can accumulate those. And then we can use the second what object to reset the counter. So now we have this running index that's telling us which of those subdivisions should we be on, or which of those new subcontainers should we be on. The 0th, the 1st, or the 2nd. I'm going to go back to 2, 3, just to keep things simple. And so now we can simply pass that into our stash object. And you can see that we're getting exactly what we hoped to. And it looks like we have a little bit of a kink here. And I wonder if that's because I have something is out of sync. I wonder why that might be. Let's see what we're getting here. Is this coming at the wrong time, perhaps? It looks pretty close. I'm going to go ahead and say this is probably correct. There might be something weird that's going on. Basically, what I'm looking at is the fact that we have this little kink in this. So there may be something slightly wrong here. If anybody can identify that, make a comment down below. But I can't figure out what it is. Another thing that we could do, another way we could do this is instead of taking the modulus, we can just do the adding. and then reset on each of the what triggers. That looks to give us a better result. So because the what triggers are telling us the points at which these new phasors start, they're a really nice place to just give us an impulse into this right inlet of the plus equals tilde that's adding up our sample values, right? This is where we're getting those super small sample values added up that have been scaled. So that's basically our subdivision container. So in fact, we could encapsulate all of this. Let's do that. Basically everything that is here. And we can call this a container. Great. And I could like put a text edit in here if I wanted to at key mode 1. And then one of the most annoying things, you always have to put a route text after text edit. Maybe there's an argument to be able to suppress that, but I don't know about it. 2, 3, or let's try another one. 2, 3, 3, 7. How about? Cool. So that's the container concept, where we've basically taken this idea of being able to have some existing container, right? And we could even like cascade these, right? We could do this. Let's do, I don't know, 4, 1, 5 and see what we get. It's pretty wild. And we can just have containers nested within containers, which is this idea of the nested tuplet. And you see, actually, sometimes we get these little interrupted pulses. I think it's basically my computer on this 100-degree day here in Los Angeles, kind of suffering a little bit. So ignore those. So now we have this container concept. We really just have one more thing to do, which is this subdivision concept. So if we go to another example, in fact, let me see if I can like get this right. Let's say like 5 here. Let's see if this is valid. Cool, it is. So basically what we're going to say here now is inside our, in fact, let's do this. I think this is more verbose than we need to be, but it will help make sense. So inside the first container, there's just going to be one event, right? So it'll stay the way it was. If I put a 2 here, we'll subdivide that second container into 2 events. And then for the second container, we're going to divide that into 5 events. Okay. And so the subdivisions, as mentioned, are different from the containers in that the number doesn't tell us how long the thing is. It tells us how many events there are going to be equally divided within a container. So now, if we were to use a really simple example, like say the number were the same for both of them, 5 and 5, right? We could just use the subdiv object. And then we could say, or subdiv 5. So you can see like it goes faster when we have the shorter container. And it goes slower when we have the longer container because it's just trying to cram that many events into that much space. The only issue is, and maybe it's not the hugest one, but the you can't tell subdiv what its division should be with a signal. So we won't use subdiv. So we're going to want stash again. And we're going to want another one of these. And each of these phasors that we get, we'll do basically the same thing we did before. We'll get a running count. So this is a running count of these phasors that have ever passed. Okay. And we don't want to be constrained to having to, like, we want to be able to have actually this subdivisions list be longer than the containers list so that it will like wrap around, which could create some interesting rhythmic results. So in this case, I think we will use the modulus, even though it did give us a little trouble last time. And we'll take the length of the input list. And very similar to what we were doing last time, we're basically just trying to get to this kind of running count of how many containers have passed so that we know what subdivision we should be using. Because we're going to pass that again to a stash. So we'll store that in a stash, and then we'll pass our counter into that object. And then a way that we could produce the subdiv object is to simply multiply the incoming signal, which is going to be this one. So the incoming phasor. We're going to multiply it by the number of subdivisions that we want. And I think I need to bang through my stuff again. Cool. And then we'll take the modulus of 1. So what we've basically done here is made like a really big phasor. You won't be able to see this. I'll make the range bigger. We'll go from 0 to, let's say, 10. So this scope is now showing from 0 at the bottom to 10 at the top. And so what we're doing when we multiply it is we're getting these longer phasors, or sorry, higher phasors rather. And then if we take the modulus of 1, then that allows us to produce subdivisions. And you can see as I move things around, I get weird stuff like these like half high. So ignore those. But you can see we're getting now these tight subdivisions. So if I do, our example was, let's do like 1, 5, like this. And I say 1, 5. I feel like we have a small issue. Dang. Let's try it the old-fashioned way. So another way to get what is to say delta and then less than 0. And you can see, so now we're getting exactly what we hoped, where on the 2 subdivision, which is the longer one, we get just 1 event. And then on the 3, we get 5. And let's hear it. So we can change our subdivisions. And actually, that's funny. 3, 5 gives us just a repeating thing. But if we do something like 7, 5, or we do 2, 5, you can see we can get some pretty cool rhythms. So like if we start to really mess around. And this is pretty fun, I think, just because we can really just mess around and play and find a rhythm that's cool. I think one benefit to this, not to besmirch Nest Up in any way, but one benefit of this is that you can just experiment with these things in real time and you don't need to hit the parse button. The other thing is this really, in a way, it's sort of more clear in that it explains things as this kind in this sort of nested fashion, right? Where you can, like, if you get into these more complicated examples, you can see there's this kind of real burrowing down like this, where you're going deeper and deeper and deeper in, and it's almost like code, right? Where you might have, JSON code or something where you have things within things within things. This is kind of a different concept where we're just counting along, right? And we're saying, first thing that happens, third thing that happens, fourth thing that happens, which creates probably a little bit less like predictable results, or sort of results that you can anticipate what's going to happen, but it does allow you to really mess around. So that's